Hey, everybody. Welcome back to episode 2 of Dark Mode, the show where we do sketchy stuff with computers. If you don't remember me, my name is Ryan Reese. I'm a senior escalation engineer on the Windows debug team at Microsoft. I say if you don't remember me because I think it's been about 4 years since I made a video, and there's a lot has happened in my life, but I've got some free time now. I'm going to try to record a video. This episode of Dark Mode is actually an adaptation of a session that I gave at work, malware you pay for. And ideally, I would like the malware you pay for series to be episodic, where we basically every episode talk about a new example. That, of course, leads me right into the question of like, what is malware you pay for? Well, that's of course it's a sarcastic term that some of us use to describe legitimate software that customers use on their machines. Enterprise grade software that they no doubt paid a lot of money for licensing to use the software to do whatever it does. And when you really start to investigate, look under the hood, scrutinize the software, you find that this software exhibits behaviors such as, API detours, hijacking, APC injection, stuff like that. Things that you would customarily see or expect from literal malware. But it's not malware; it's legitimate enterprise software that was very expensive. Um, so I just find that really fascinating. So I want to cover one such example of that with you today. And there's going to be a lot to unpack here. So without further ado, I think we can go ahead and get started with this. If you look at the middle of my screen, what you see here is a virtual machine, obviously, in my lab. And well, this is a Windows domain controller. It's a Windows Server 2022 domain controller. And don't worry if Active Directory is not your cup of tea. That's fine. This is not actually going to be an 80 session at all. It's just that Active Directory happens to be my forte. So when I'm telling a story, odds are that it is going to involve Active Directory domain controllers at some point. But don't worry, this is actually just a Windows internal session. So we have a Windows Server 2022 server here, right? And on this server, we have Active Directory, which I'm going to take a look at here. And we have a user. His name is Terrence McSwiggan. That's our user in Active Directory that we're going to query. And I have this PowerShell script here. I'm going to go ahead and open that. And I would kind of like to frame this in the context of an actual customer case. A customer may open a case with support for any reason, anything that they might want to investigate on their domain controllers. It could be performance related. It could be that just something is not working correctly. It could be a crash. It could be whatever, right? Any problem. It's not that important in the context of what we're going to discuss here. But if anything, let's go with performance. So I have this PowerShell script here, and I'm just zooming in to make it easier for you to see. This PowerShell script runs get AD user, which you're probably familiar with, and it runs it 200 times in a loop, calling get AD user just simply to get the SAM account name of this Terrence McSwiggan user account. And the reason I run it 200 times in a loop is just because, like any other database in the world, Active Directory has, caches. You have to make sure that the caches are warmed up. You have to make sure that all the right pages are paged in. And so I do run the query a bunch of times, and then I take the average of all the queries just to, try to eliminate any sort of like noise or outliers, things like that. So let's go ahead and run it. You'll see that first one like hangs for a long time for some reason. All right, so the script says that the average LDAP query performance over 199 runs, because discarded that first one that took like 5 seconds. But the average of the remaining 199 runs was about 17 milliseconds. And we can go ahead and run it again just to see. I didn't get the long delay on the second time around. This time we'll see that the average of my 200 runs is now 17.1 milliseconds. So look pretty consistent there. The problem is that I know that this figure is not accurate. I know that this query did not actually take 17 milliseconds. And the reason I really know that is because I'll switch over to the event viewer right now. I already have the instrumentation enabled that comes with Active Directory. It has some instrumentation in it that will has the ability to log every single LDAP query that it receives, and including that. And here's the event. You can even see, you can verify that, yeah, this is the LDAP query that's querying for the same Terrence McSwiggan user. And if I scroll down, you can see that this LDAP query took 0 milliseconds. It was actually much faster than 17 milliseconds, 0 milliseconds. So the query, we know that LDAP query didn't literally take 0 milliseconds. It took some amount of time. It's just that this was a sub-millisecond query that took something really close to 0 milliseconds. So what I gather from this is that PowerShell is just not. I won't. I don't know if I would blame PowerShell as much as I blame Active Directory web services, which is what Get AD user goes through. Adds a ton of overhead and is just not does not have the level of precision that we need to really explore this. So forget that. What I did instead is I wrote something from scratch. I wrote something to make more detailed measurements. And I'll go ahead and run that now. And there it is right there. And we'll look at the code in this. Actually, we'll look at the code right now. Let's go ahead and look at the code. So I have it here. Okay, let's go ahead and make this full screen. So, I wrote this code and it's really simple. Um, it's really simple C. So this first function called estimate TSC frequency, it's really not all that important. It's simply a custom, a function that I use to estimate timestamp counter frequency I that makes more precise and makes measurements a little bit more precise than using the built-in Windows API function, which is called query performance frequency, right? Yeah. So query performance frequency is what you would customarily use in conjunction with query performance counter to take measurements. And query performance counter is really just a wrapper around RDTSC. If you look at the documentation on MSDN for query performance counter, it'll say, you should use query performance counter. Don't use RDTSC. But the truth is that 99.99% of cases, it ends up being that query performance counter is nothing but a wrapper around RDTSC. So there really is no reason to use. And in fact, I would say that it is preferable to use RDTSC in most cases. Anyway, query performance frequency also has a problem on the Windows platform, where it returns 10 megahertz no matter what. Like, I guess it's hard coded or something. I don't even know. But it doesn't matter what kind of processor you have. It doesn't matter whether, what kind of anything. It always returns 10 megahertz, which is not even within within orders of magnitude of your actual timestamp counter frequency, which is the base clock of your processor. So the like for example, this processor that I'm on now has a base clock of something like 3.1 gigahertz, has a boost clock up to 4 gigahertz, but the timestamp counter always runs at the base clock of the processor. It's an invariant TSC, so it always runs at that frequency, no matter what sort of boosting or throttling may be occurring elsewhere on the CPU. So 10 megahertz is a extremely imprecise number. And because of that, I don't like to use it. I like to instead measure it myself. I essentially just, take an RDTSC, uh, take an RDTSC at the beginning, and then I count for exactly 1 second. And then I take another RDTSC at the end and I see, how many ticks did my processor how many times did my timestamp counter increment during that 1 second interval? And that will give me a very close approximation of the processor's base frequency, which is also the timestamp counter's frequency. All that is to say that I like that because it's a little bit more precise than what is built into Windows. Now back to the LDAP stuff, you can see that I'm, simply calling LDAP on localhost. This is a domain controller that is doing an LDAP query locally against itself, right? And of course, it's just a lab. It's just a POC, a proof of concept, right? So I'm just hard coding in these, stupid credentials here, doing a simple bind. No big deal. It's just a lab. And then I'm going around, and then I'm going on forward and doing these LDAP queries, the exact same LDAP queries. I'm getting the user, and I'm querying for just one attribute, which is SAM account name. And I think I'm doing that maybe 500 times. Yeah, 500 times in here. All right, so there we go. Of course, I'm going to win because I'm going to win compared to what you just saw uh, with PowerShell and Active Directory web services, because I'm not processing the results in any way. I'm simply issuing the query and then completely ignoring the results. So it's going to be as fast as absolutely possible. Yeah. So with that, we can go ahead and run it on this machine right here. All right. So what we saw there, we saw a couple of interesting things. You'll notice that as soon as I hit enter, there was a slight delay, and there's a delay of like 1 second. Well, I say like 1 second. I actually mean a delay of exactly 1 second while I do that thing I was just talking about, where I calibrate the timer, right? And then of course, this is my estimated TFC frequency, which is just so happens to be 3.31 gigahertz. And then I issue my 500 LDAP searches, and we see that each LDAP search took an average of 444 microseconds. So when you're measuring stuff with this amount of precision, when you're measuring things that occur on this tiny of a scale, this microsecond scale, um, any sort of perturbance is going to throw your stuff off. Like depending on what's running in the background, antivirus could be running, another service could be, doing something stupid like downloading Candy Crush from the Microsoft Store in the background. All of these things go on in the background in Windows. So um, it's so easy to throw these numbers off. So it's best to just test this a bunch of times. So, so for example, we just ran it again and we've already reduced it to 390 microseconds. We ran it again. Now we're down to 332 microseconds per LDAP query. All right. So 349. All right. So we'll go with that. Somewhere in there is the real answer is somewhere in there. So at least we know we're in the right ballpark, like not even close to 17 milliseconds, right? Like that's not even close to the right answer. All right. So now that we've explored that, what I'm going to do now is I'm going to install some third party software. And that's the third party software I'm going to install. And I'm not trying to like trash talk it or bad mouth this third party software because like I said, it's legitimate software that customers use and pay a lot of money for. And I'm not trying to say it's terrible. And that I'm not trying to say that you shouldn't use it. I'm simply just gonna like lay out the facts of like what it actually does because I find it quite fascinating how it accomplishes its end goal. So with that being said, I'm just going to install it. Now, I'm not going to configure the product in any way. So the actual intent of this product, I mean, this product does a lot of stuff. I mean, there's a lot of things that it does, but one of the main things that this part of the software does is that, well, it's an auditing suite tool software. And one of the things it's going to do is it's going to audit every incoming LDAP query or LDAP operation that hits this domain controller. And it's going to, send that to some centralized logging system, SIM system or database of some sort of centralized repository where everything can be, queried and bubbled up into this really nice looking dashboard. And, like, so you can get more detailed insights into like exactly what's going on. Um, with your, Active Directory environment. So anyway, we're not going to configure any of that stuff today. We're just simply going to install this agent and nothing else. We're not going to point it at a database. We're not going to do anything. We're just going to click next, 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 install, and let it go. Completely unconfigured. And now that's finished. And so the first thing that I want to point out is that now that the software is installed, I'm going to do a task list /m, and I'm going to specify the name of a third party module. And you'll see, let me go ahead and increase the font size to make it a little easier to read. You'll see that right now it's not returning anything, but that's okay. You just let it cook in the background. You just let it cook. And then eventually there you see it did finally work. After some delay, you'll see now that the lsas.exe process has loaded this third-party module, cadhook.dll, which stands for, change auditor for Active Directory, whatever. Okay, so now, I mean, first of all, it's interesting. How did lsas.exe load that DLL in the first place? Right? That's weird. And secondly, like what does it do? How is it interacting with Active Directory? So let's go right back to our LDAP searcher program and run it again. And we'll see that the timings really haven't changed much. 348 microseconds, 313 microseconds, which is actually the best result we've gotten yet. And then, oh, here's a big one, 484, 297, 385. All right. So It doesn't seem to be affecting performance very much right now, but remember, this is the best possible case because the software is not configured whatsoever. So it is doing the software is doing absolutely nothing right now. So this is the best possible case. There are other factors involved as well, which is kind of why I prefaced all this with when you're measuring things at this tiny time scale, there are so many different things that could be happening. Like, for example, if I wanted to be more precise about this, I probably would disable any sort of like boosting on my CPU before I tried to do this benchmarking stuff. Uh, but that's okay. We're going to look at it in another. We're going to look at it from another angle. Let's say, just for the sake of argument, that these numbers did go up a little bit after installing this software. And you might say, who cares? Nobody's going to, you can possibly notice a difference about, from an LDAP query taking an extra 100 microseconds, right? Like that's a tenth of a millisecond. Who could, like, you would never notice a difference in that, right? And I would say for 99% of people, that is true. However, I want to show you something. I want to show you this picture right here. So this screenshot, obviously I had to redact a lot of things, a lot of server names and stuff, because this is a real life screenshot of a dashboard. And this dashboard corresponds to just one of the data centers. And this is a graph, like a performance monitor graph of uh, LDAP searches per second. And you'll see that there are multiple servers. There's like 30 servers here or something in this cluster, right? And they're all just doing LDAP all day long from people all over the world. And you'll see that this caps out these servers, at least this server especially, is capping out here at about 30,000 LDAP searches per second. And I'll let you do the math on that. But imagine if you want to sustain that amount of throughput, if you want to sustain 30,000 LDAP searches per second, each individual LDAP query it cannot take very long, right? It has to be really fast. And if you increase the length of each LDAP query by 100 microseconds, 100 microseconds times 30,000 per second, right? That's a significant drag. That's going to be a significant drag on the total amount of throughput that you're going to be able to sustain in these high performance types of scenarios. So, uh, and I've seen multiple customers who really are driving their race cars in the red in terms of, how far they can push Active Directory and LDAP server in particular. So these numbers are not crazy. I've seen these kinds of numbers both inside and outside of Microsoft. So yeah, that's why it can make a difference if are if you're busy enough, if you're running a big enough operation. All right. So the next thing I want to do is I want to explore what this looks like from uh, basically under the covers, right? I want to see like what this module is doing in here. Are we interacting it with it in any way? Is it interfering with anything? What does it look like? So for that, I turn to Windows Performance Analyzer. And now Windows Performance Analyzer, you can get, uh, let's see here. We'll look at you later. Uh, Windows Performance Analyzer. All right. So I think you can get this on the Microsoft Store. I think you can get it as part of um, the debugging tools for Windows and things like this. I think there are a couple different ways you can get it, but it comes with two parts basically. You have the Windows Performance Recorder, WPR, Windows Performance Recorder, which a long time ago used to be called XPerf, but now it is called WPR, Windows Performance Recorder. And then you have WPA, Windows Performance Analyzer, which is what you use to open the traces that are generated by the recorder. I just so happen to already have these traces generated. I already generated them earlier before starting any of this. You can see that the title of this one, if I can zoom in correctly, is called before ca.etl. So this is the normal baseline trace, I guess you could say, from before I installed the software. So I expand this computation section and I go to CPU usage sample. So you'll see that, well, there are basically two main graphs that I ever want to look at in here, which is CPU usage sampled and CPU usage precise. Now, I personally don't ever really find a use for CPU usage attributed. Somebody might, but these are the only two that I really use. And they answer two different questions. The first one I'm going to look at is CPU usage sampled. And I'm going to expand that. All right. So this trace was taken. Well, instead of telling you, why don't I show you? It's really just this simple. I'm going to go here. All you have to do is type WPR, and WPR, I believe, is packaged with Windows these days, so you don't actually have to download anything. WPR comes with Windows. Yeah, so WPR, I believe, comes bundled with Windows these days. So you don't actually have to download anything new just to get WPR. You only have to download WPA to analyze the traces. So anyway, that WPR dash start space CPU, that starts the trace in the background. Run your test, your repro, and you'll see that the time that it took, it went up a little bit, right? Just because WPR, it does have some overhead involved in it. And then you type WPR dash stop, and then you give it a name like, uh, before.etl. And that's all there is to it. When you do that, you'll get, a WPR, WPA trace, Windows performance trace like this. And then you go to, yeah, make sure configure your symbol path, and you can see that my symbol path is configured. This is the, public symbol server. You don't need private symbols for anything in WPA. Public symbols work just fine. So here we are. So what I'm going to do is, I know that the activity I'm interested in is right in this area here. I have this pink line that shows this weird plateau, and then I have this yellow uh, stuff here that kicks up briefly. I know that this is the LDAP searcher activity that I'm interested in, so I'm just going to highlight that and I'm going to zoom into it. There we go. And we'll see that, okay, so this pink line, where I'll zoom in, this pink line, and there's this plateau here in pink. And this plateau represents, my LDAP searcher client application. It's spinning one of the processors at 100% during that estimate TSC frequency function. It's to calibrate the timer, right? So I already know what that is, and I'm not interested in that, so I can skip that and go over here. As soon as the timing stuff is done, then this yellow stuff kicks up, and that yellow stuff is lsas.exe. That's our LDAP server actually responding to the LDAP queries, right? And so, in fact, I can just click on lsas.exe, since that's really the only process I'm interested in right now, and just filter to selection, right? And then I'll move that bar out of the way and I'll start expanding. Fortunately, it should already be sorted by uh, the most heavyweight stuff will already be sorted at the top. So you don't have to worry about sorting the stuff. It should already be sorted. And then you have a call stack here. So this first call stack is going to be your most heavyweight call stack, which means, the call stack that was on the processor the most during the time of this trace. And of course, we know what it was because we just ran this test ourselves, right? So we have an LDAP query. Of course, it's going to come in on NTDS ATQ pull thread, which then goes to a LDAP connection, IO completion sort of thing. And then we have like, search request here. This is very normal. Like this is what it should normally look like, right? A normal LDAP search request. That's what this is saying. The other question is, well, actually, we'll talk about the CPU usage precise graph after the next part. I took another trace, which is the after ETL, after CA ETL. So I'll just pop that open, make sure my symbols are loaded. There we go. Now this is the same exact trace, only it's after I installed that third-party software and I ran the exact same LDAP searcher thing. So the first thing I'm going to do is I'm going to look at the CPU usage sampled graph. I see the exact same activity here that looks practically identical. I'm gonna just go ahead and filter this to LSAS because it's all I care about right now. I'll just zoom in for the heck of it. Zoom in. Right. So here's my LSAS LDAP server activity. And then here, and I'm sorry if this text is kind of small and hard to read for you, um, but you can pause the video and look closely if you want. I'm going to go ahead and expand out this call stack, which is the most heavyweight call stack here, right? Here we go. So you can see it looks a bit different this time. Same thread start, of course, starts off with an ATQ pull thread, which is what catches our LDAP queries coming in from the client. But then all this weird third party stuff happens, right? Like all of this, right? cadhook.dll. And then after all the cadhook.dll stuff is done, then it drops us back off at ATQP process context as if nothing had ever happened, right? Um, like we should have gone from ATQ pull thread directly to, we should have gone from ATQ pull thread directly to ATQP process context, but somehow this CAD hook stuff injected itself into the middle of our call stack. And because we know what the software was designed to do, it's designed to intercept all of the LDAP queries that take place on this domain controller and save certain bits of information about the LDAP query. But then after it's done doing its business, it has to allow the domain controller to finish, processing and responding to the LDAP query as normal, so it doesn't interfere with anything else, right? But this is quite perturbing because there's no legal way, for him to have gotten in here. And what I mean by legal is that it's not there's no method of injecting yourself into this process that is supported by Microsoft. Unsupportable. Uh, there's no callback model here. There's no plugin model here. There's nothing that would have allowed you to accomplish this in a legal sort of way. That being said, we still end up supporting it a lot of times, or supporting scenarios in which the software is present, because even with the software present, it may not be the root cause of the issue. A lot of times it's not causing any issues. So we have to just live with it here. But I'm still extremely curious about how this got here, right? And so before we leave WPA behind, there's one last thing I wanted to show you, which is the CPU usage precise graph, which, so this basically the difference between CPU usage sampled and CPU usage precise. What is the difference? Well, CPU usage sampled, of course, uses, as the name implies, I should say, uses samples. Like it samples the CPU every, I don't know, maybe 1 millisecond, maybe 10 milliseconds, something like that. It samples it and says, what are you doing right now? What are you doing right now? What are you doing right now? Right. So it samples the processor at like a monotonic rate, and and it uses that to deduce, like, okay, here is what you were computing most of the time. In contrast, we have the CPU usage precise graph, which is similar but different. So the CPU usage precise graph uses, it basically inserts instrumentation at every context switch of the processor. So one of the things that this graph can answer is, let me just zoom in on my LDAP activity, which is right here. I'll zoom in on it so a little bit more. Sorry, instead of that, I'll just zoom in on LSAS, because that's all we really care about is LSAS. And so then let's see. I need to add a, do I have my symbols loaded? Yes. I need to, here we go. Here we go. Expand, maximize. Uh, okay. Let me expand this a little bit more. Sorry, just getting this into a good view. Okay, so this is a good view to explain what I wanted to explain. NPDS ATQ pull thread is the beginning of every LDAP search. You can know for a fact that every LDAP search that happens on your domain controller is going to begin its life at ATQ pull thread, right? And so all of my LDAP searches combined used 83 milliseconds of CPU time. Now, here's my CAD hook stuff right here. And all of the CAD hook stuff all combined used a total of 2.29 milliseconds. So I'll let you do the math on this again, but basically 2.29 milliseconds into 83 milliseconds gives us something like, I don't know, 12% or something. So basically, if you wanted to know how much time, how much processor time, how much CPU time is this third-party software stealing from me, basically, or how much is it using, how much is it sapping, there's your answer, right? So it's small, but not nothing. Small enough that most people don't really care, but it can be an issue if you're really busy and trying to achieve really, really high throughput. So that's it for the WPA stuff. So I can close that. Now, I still haven't answered the question of how did CAD hook get there? So my first, instinct there was to use TTD, time travel debugging. Time travel debugging it used to have an internal name of IDNA. A lot of old timers inside of Microsoft still call it IDNA, but it's rebranded now, has a new name. It's called time travel debugging, and it's public. You can, fire up WinDBG, which you can get from the Microsoft Store. I think they're still working on a standalone version of it. I don't know. Maybe they already have it, but you can do launch executable. You can do, launch your executable here and then click this button here that says record with time travel debugging, right? Configure and record. And, in case you're not familiar, think of it as, well, with a memory dump, you're basically just taking a snapshot of that process, whatever was in the memory of that process at that particular moment in time. Whereas with a TTD trace, it's like a, a DVR recorder, right? Like where it's recording the process that gives you an added dimension of time. And it can make a huge amount of difference when you're investigating something complicated. Because it's like when you're trying to solve a crime, it's like the difference between having a photograph of the crime scene versus having a surveillance camera footage of the crime as it happened. You obviously can tell which one is preferable in that situation, right? So I go, for time travel debugging traces a lot for situations like this. So before I show you that though, I'm going to show you this one, LSAS before CA dot run. So this is a time travel debugging trace that is before the third-party software is installed. And I only want to show you this to demonstrate one thing, which is that, again, imagine this in the context of I'm trying to solve a problem. A customer has a complaint about something, performance, or something that's not working correctly, etc. I set a breakpoint on something, and then I hit G to go, right? Just like in your debugger, you hit G to go. And then when I hit enter, just like that, in less than 1 second, I was able to traverse all the way from one side, the beginning of the trace, all the way to the end of the trace, just like that. Now, with that in mind, I'm going to go to the LSAS O2 after CA time travel debugging trace. And this is after I installed the third-party software. The first thing you'll notice right off the bat is that now where I have this timeline that is supposed to show me exceptions, right? This is supposed to be a built-in little timeline of exceptions. Now I get these spinning dots right down here, right? And it's just going to keep going and going. I don't know when it's going to stop. Um, Kind of strange. But now I need to set a breakpoint on something. And I know what to set a breakpoint on because we saw it in the WPA trace, right? It was like BP, which is, set a breakpoint. Sorry, I'll try to increase my font a little bit here too, just to make it easier for you to read. BP NTSATQ is the module, and then it was what ATQB process context, right? And then I'll hit G for go, assuming that I'm going to hit that breakpoint. But before I do that, let me actually disable the breakpoint first and just hit G and to go, just like we did in that first one. Okay. And right off the bat, you'll notice that something is very, very different. Now I'm getting this crazy amount of spew that's spewing these messages at me: illegal instruction, illegal instruction, illegal instruction, illegal instruction, over and over and over again. And this actually makes the time travel debugging trace run orders of magnitude slower. I'm talking at least 100x slower, maybe even like 1,000x slower. Super, super, super slow. I have worked customer cases where I've had, this install on a domain controller. And just imagine, this is a lab domain controller that is, you know, almost nothing going on. Imagine if you tried to do this on a busy domain controller. Imagine if you tried to do it on one of those domain controllers that we looked at in that perfmon screenshot that was doing 30,000 LDAP searches per second. Each one of those LDAP searches is now triggering this weird illegal instruction thing. I'm going to go ahead and stop it here. But I've worked customer cases where I've set a breakpoint. I didn't even care that this software was installed. It just so happened to have been installed. And I would set a breakpoint on whatever I was interested in, hit G for go, and then I would just walk away and go to sleep and wake up the next morning and come back to my computer the next morning and find that it was just still running, trying to find that breakpoint. Like, it hardly made any progress. It made a little progress. It is making progress. It's not like stuck or hung. It is making progress. It's just excruciatingly slow progress. And so a lot of times when I'm working with customers, this is when I'll say something along the lines of, listen, Mr. Customer, you have this particular software installed. And while I'm not blaming this software, I'm not saying that this third party software is the root cause of your problem. But what I am saying is that it being installed is hindering debugging efforts. It's making it impossible for me to really debug the issue. It's obfuscating my debugging efforts. And so, can you please get out of there? And then, of course, coincidentally, there are some times when they uninstall the software and the problem goes away. But there are other times when, it really had nothing to do with the problem. It just made debugging, especially time travel debugging traces, much more bearable, because this is not bearable. It's awful. We're going to explore like what exactly all this means and why it's doing this here in a second. So, all right, so back to my break point, which this is just coincidentally what I wanted to break on. Um, if I do a U for unassemble and then paste in that function name and take a look at it and see what I see, um, this immediately jumps out at me as odd, weird. When I first started mentioning that there was some sort of detouring or hijacking going on, you may have you may have jumped to the conclusion that, it's probably just going to be a jump instruction, right? Like, you can do an unconditional jump somewhere and jump to somewhere in your code and then jump back. But this was much more unexpected to me. And if you haven't caught on, it's this very first CPU instruction that stands out like a sore thumb. Like, this is not supposed to be here, right? And the question is, what is it? Like, UD2? What even is that? It's not a CPU instruction that's commonly used. Uh, and it definitely should not be here. Also, I want you to notice that the CPU instruction is 2 bytes long. That will become important later, right? So keep in mind that the UD2 instruction is 2 bytes long. Um, so your CPU, these are just like the friendly names for the is assembly instructions, right? Your CPU doesn't actually execute this stuff. Your CPU is actually executing this like stream of bytes, right? And of course, they correspond to these friendly names, right? But your CPU execute basically, think of just this stream of bytes going into your CPU, and there's no new lines, right? There's an encoding scheme that your processor knows that, like, okay, I see this many bytes, and I know that I've reached the end of the instruction, and that I know that the next byte that I read will be the beginning of a new instruction, right? Uh, there's no other indication. Like, an instruction could be, it could be 1 byte, it could be 2 bytes, it can be 5 bytes. So, um, what even is UD2? So we go over to the Intel 64 and i32 architecture software developers manual, which, um, if you'll notice, is actually a 5,000 page long PDF. It really is 5,000 pages, and it will tell you almost everything you ever wanted to know about the Intel CPU. And in fact, even searching this thing can be quite I'm probably going to have to fast forward this part because searching through this thing is, um, found another one. There it is. All right. So, it literally stands for undefined instruction. And you may have thought, well, if there's a UD2, is there a UD1? It turns out, yes, there is a UD1 and there's a UD0 as well. The difference is that UD2 is the first revision of this instruction that was implemented consistently across all processors such that you can use it reliably regardless of what kind of processor you have. No one ever uses UD0 or UD1, to my knowledge. It's always UD2. So what does it do? It literally, all it does is raise an invalid exception. All it does is create an exception, right? Let's see. I'll go ahead and let's just use this as scratch space. We'll go down here, get this out of the way. So you might have seen like some old programmers, which is me. I am old programmer, um, doing something like this in their code, right? Which, if you look at this, you'll see like you might be like, oh, this is obvious nonsense. It's going to crash if you run this because you're trying to write to the memory address of zero, right? Or well, you're trying to dereference memory address zero. I mean, it's not going to work. It's going to crash 100%, right? And so you might actually see this wrapped in an assert macro. Um, and the intent is to intentionally crash the program. And it's typically done as like an assert mechanism. Like if this value or the state of your program is not in an expected way, then you intentionally crash the program. The problem with this approach is that it's old fashioned and it's outdated. And if you have an optimizing compiler, there's no guarantee that your optimizing compiler won't optimize this line out because your compiler will see that, hey, this is obvious nonsense. I can just get rid of this, right? So there's no guarantee that it will, work, especially if you're compiling, with optimization enable. So in contrast, if a UD2 instruction, in contrast, will be guaranteed your compiler won't mess with that. So this is preferred if you're trying to intentionally crash your program for debugging purposes. In other, like in Plain, for example, you might see something like built-in break, I think it's called. And that's just a wrapper around UD2 as well. Right. So, all right. So let's go play with UD2 a little bit. First, I'll open up Visual Studio and create a new project. Empty project is fine. And I'm going to call this, I don't know what I'm going to call this. UD2 test, create. And I try not to use Visual Studio anymore. But in this particular instance, I find that it's a good visual aid. So I'm going to use it right now. Create a little source code file. I'm going to increase my font size. We're going to do include here, include those. I'm going to do include stdio. I'm going to do include intrend IH, right? And then do my making. Right. And then so I'm going to do a printf statement here that says before the exception. And then on this line, I'm simply going to call UD2. And that's it. Now I'm just going to hit play. This is going to run the program. It compiles it, runs it. Let's go. And we will see once that happens. Oh, it's got to load some symbols. All right. So we'll see that, it printed our line. And then in the background in the debugger, it says, we crashed, right? We crashed as soon as the program crashed when we hit that UD2. And it crashed at, this address. This is the instruction pointer right here. And then, we crashed with this code, which is the illegal instruction, with the same exception code we saw in the TTD trace. Interesting. Problem is like when you hit continue, like you can't continue. This is not a, you can't recover. You cannot recover from this, right? No matter how many times I hit this continue button, it's just going to keep blocking me here at this UD2. You can't get past it, right? So now I'm going to introduce to you an interesting little trick called set unhandled exception filter. Windows 30, Win32 API function where you can actually set the unhandled exception filter for your process. The Windows operating system obviously gives your process a default one. Like by default, you have your basic unhandled exception filter that will, crash your process. Uh, this typically goes straight to like Windows error reporting. If you have like proc dump installed, it may, go to proc dump, various things like that. Set unhandled exception filter is publicly documented. Set unhandled exception filter. You go here, you read the documentation. You'll find that you have to, you supply your own exception filter. It's a user supplied exception filter. Importantly, you have to remember that, and it says so, the unhandled exception filter function gets control and the process is not being debugged. Okay, so if you read this documentation, it basically tells you that this behaves differently depending on whether a debugger is present. So we're for this next part, we're going to have to execute this outside the context of Visual Studio, the Visual Studio debugger. But I'm getting ahead of myself. I have to actually create my unhandled exception filter first, and I'm going to call it, my filter. Sorry. So then to actually implement it, we have to do like, I don't know, static long callback my filter, right? And then it takes in a data structure, or more accurately, a pointer to a data structure called exception pointers. Right. All right. And now we've done it. So what's going to happen now is that when I hit my exception, it's now no longer an unhandled exception. I'm handling it right here in my filter, right? And so there's a couple things you can return from this. Um, Normally, the thing that you return is like exception continue search is what you normally exception continue search. Did I spell it right? Yeah. So exception continue search is what you normally return from your unhandled exception filter. And it tells the operating system to just basically keep passing this exception along to the next exception filter, because you can have multiple exception filters installed. That's the whole idea behind the structured exception handling system, which you can, Windows, uh, structure exception handling. All right. We can search that. You can read all about it right in here. Structured exception handling. There, the same stuff. So, and I'll let you read that on your own time. But what we're actually interested in something else here. We're going to return exception continue execution. So what this does is it tells the exception filter to instead try to return back to our program and continue executing. Now, the point behind this is that if you're going to try to continue executing your program, the assumption is that you've done something uh, that you've done something to remediate or fix the exception. You've changed the state of your program such that the exception will no longer occur. And this may not be a UD2. It can be any exception. It can be an access violation. It can be a divide by zero. It can be, whatever would cause any sort of exception. Right. But in this case, we have not done anything to our program. The exception will occur again. Um, So here I'm gonna write in another printf just to prove that we are actually calling, our exception filter. I'm gonna say hello from inside our exception filter, right? And then I'm gonna compile that. And now I need to run it. I'm gonna run it from. Let's get out of here. Let's get out of here. Let's increase this font size a little bit so you can see it. Oh, I named it UD2 test. Sorry. Right. So x64 debug. All right. So then I run it. We'll see what happens. You'll see now that we have an infinite loop, right? It just keeps saying hello from inside our exception filter over and 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 over again. Infinite. Why does it do that? Because we are basically bouncing back and forth between here and here, bouncing back and forth between here and here. Uh, we hit UD2, which throws the exception. We catch it here, and then we try to return. The problem is that we return back right back to our UD2. And so we can never get past that UD2. But what if I told you that there is a way? And the way we do that is inside of our exception handler, exception filter, we have this data structure full of pointers, right? And it contains all sorts of, well, it basically contains the state of the processor at the moment that the exception was generated, including the contents of all the registers, right? RAX, RBP, RBX, RCX, RDI, all that stuff, including the instruction pointer. And guess what? We can actually modify this exception pointer. What if I incremented our instruction pointer by 2? The reason why I chose the number 2, I chose to increment the instruction pointer by 2 bytes is because remember from our previous look at UD2, right? The instruction is 2 bytes long. So if I move my instruction pointer up by 2 bytes, I will basically be skipping over the UD2 and I'll continue executing at the next function. I'm sorry, the next instruction, right? And so just to prove that that works, I'm going to go back to main and I'm going to go after my UD2 function and I'm going to say after the exception compile run, and there you have it. It did exactly what I said it was going to do before the exception. We are inside of our exception filter. We modify our instruction pointer by making it skip 2 bytes. Then we return execution to our program and we can just keep running as if nothing ever happened. Pretty cool stuff. That's basically what that third-party software that I installed on my VM earlier is what it's doing. It's a little bit more complicated than that. This is the very rudimentary version of that, right? Basically. But what I want to show here is like, how can we use this for evil, basically? Because after all, this is the dark mode channel, right? Where we're supposed to be doing sketchy stuff. So we will indeed do some sketchy stuff with this. And the idea behind this is, because this is how this ties into the theme of malware you pay for, because we're going to use this uh, to write malware, essentially. And this is what, this enterprise software is doing too. Very interesting. I'm going to go ahead. I guess I'm probably done with Visual Studio at this point. Let me go ahead and I've developed some more code here, and let me back up and then go back to your VM2. So the next thing we're going to do is take a look at the code that I wrote, which is in the apps directory. And so in here, this is my little proof of concept code, and you'll see that there are 2 components to it. There's an install and there's a DLL. So the install is an executable whereas the DLL is, well, a DLL. And then, they have two separate build commands for that. I'm using the command line clang to build these, but it doesn't matter. Do whatever you want. Um, let's take a look at the code. So first, the installer. I'll go through this a little bit, but I won't go through it in like gruesome detail because at the end of the day, it's just DLL injection. And it's the exact same kind of DLL injection, if I remember correctly, that we discussed in episode one of dark mode. Dark mode episode one was like 4 years ago. So it's been a long time. I don't even really remember that well, but I think it was the same, uh, covering DLL injection. So what I'm doing here, and I'll post all of this code to my GitHub so you can play with it yourself. But all I'm doing here is, of course, you have to run this installer as administrator. It's going to enable the debug privilege, right? Which is just like this, enable debug privilege. And then um, we're going to automatically, with this stuff, we're just automatically finding the LSAS process, finding the PID of the LSAS process. Um, then we are allocating a page, of remote process memory using virtual alloc ex. And we're doing this to allocate some memory in the remote process being LSAS in this instance. Uh, and then what the next thing we're going to do is we're going to use write process memory to write something in there. And the thing that we're writing is actually, you know, the fully qualified path name of the DLL that we want to inject. Simple. And then lastly, the last step of this is to call create remote thread. And create remote thread, we're creating a new thread remotely in the LSAS process. And the start address of this thread is going to be the address of load library A, which we know every process is already going to have that, right? Because they all have NTBLL loaded, like every process does, right? So it's going to know where load library is. And then the argument that we're going to supply to the load library function is the string that we just wrote into the process earlier. We have to do it this way because, every process gets its own virtual address space, right? So LSAS, the string has to be transmitted into the private process memory of LSAS first, right? Because you know the string in this program, LSAS is not going to be able to read that, right? So you have to put the string into LSAS private memory first, and then we call load library with that string as an argument, and off we go. By doing so, have we have coaxed, we have coerced the LSAS process into running load library with our custom DLL, and that sums it up for the installer. That's what the installer does. Okay, so now let's take a look at DLL.state. This is the other part. This is my DLL, where basically I'm doing the same exact stuff that we just talked about. Uh, Obviously, exporting DLL main like any good DLL. When your process calls load library, you are essentially forced to run the DLL main function of whatever DLL that you are loading, right? So again, we're essentially, by doing what we're doing, we're forcing LSAS to run whatever arbitrary code I want from my DLL main. Now I know you're not really supposed to do anything useful or involved inside of DLL main because it's easy to cause loader lock bugs, deadlocks where basically you're trying to load a DLL, but you can't because your thread currently already holds the loader lock, et cetera, et cetera. But this is just proof of concept code. It's not like production quality code. It's just a proof of concept. I figured as long as we're hacking or doing dirty stuff, why not do it all in DLL main, right? So that's what we do. So when LSAS loads this DLL, I'm using output debug string here. Um, Obviously, in a real world situation, you would do something else. You could write to a log file. You could, upload stuff to a database. You could do whatever you wanted. I'm just doing output debug string as a proof of concept to show you that it's working. Um, and then, of course, I use the same set unhandled exception filter function, which we've already talked about. This sets the unhandled exception filter for the entire LSAS process, and it sets it to my custom exception handler, which I've called in here, I've called it get hacked exception filter. All right. And so then after that is set, the next thing I'm going to do is, and remember, we are executing within the context of LSAS right now. The next thing I'm going to do is I'm going to locate system function 7, which is exported from the crypt SP module. System function 7, if you're not familiar, it's as old as Windows NT itself, right? System function 007. Uh, it's, sure, Warren API. It's fine. This function, everyone knows about it. It takes in a Unicode string and it spits back out an MD4 hash. This is a very old-fashioned function, but it just so happens that it is still in use today. Anytime a user on a local user account on the workstation changes their password, they're going to run through this function right here to transform their plain text password into an MD4 hash, right? So here we go. Right. So then we find this, which again, I know that like this is not going to create a deadlock because I know LSAS already has crypt SP loaded. So I know it for a fact it's not going to have to load a new DLL here. So it will not cause a loader lock bug. Um, and then now that we have the address of crypt SP bang system function 7, now we're going to do something really cool. Um, I have an array of bytes here and it's 5 bytes. Basically, it's 0F, 0B, which you may know by now is the UD2 instruction. And then I have to fill it in with three more bytes, which these are not instructions. These are do nothing instructions. Um, and I have to do that for this reason. Let me go back over here and I'm going to open up this memory dump before BA. So is that what I want? Yeah, sure. That'll work fine. All right. So let me load this, make it the font size bigger. I'm going to unassemble crypt SP bang system function 7. Okay. And so this is this is an unmolested version of system function 7. It has not been modified in any way. You can see the very first instruction here is a 5-byte instruction, and it translates to we are moving the value of RBX into whatever memory address is represented by this thing, RSP plus hex 18. And so this is a standard function prologue stuff. And I assume that what this means is we are preserving the value of RBX so that we can restore it at a later time whenever we're returning from this function, right? But when I was tracing this originally, what I found is that RBX at this particular moment, RBX was already 0. And this location on the stack was also already 0. And so what that told me was, I don't think these 5 bytes here are even really necessary. I think I can overwrite them. I'm just going to stomp over these first 5 bytes of system function 7. And so that's exactly what I did. right? And I can do so without causing any like unintended effects, like accidentally crashing LSAS or whatever. So that's why I'm writing 5 bytes here, is because I'm replacing 5 bytes. And like I said earlier, the way that your CPU decodes these instructions, the number of bytes is very important, right? So if if you're going to overwrite 5 bytes, you have to replace it with 5 bytes. You can't just do 2 bytes that it takes to say UD2. And then because these next 3 bytes are going to come in, they're going to translate to something unrelated. And then LSAS will crash and then you fail. So the next thing we're going to do is we're basically going to remove the protection from that memory of system function 7. We're going to literally just copy in our 5 bytes using memcopy at the address of system function 7. And then we're going to just put the memory protection back on it, which I don't even know is even really necessary. I'm just, doing it. And then, I tell you that it's been patched. And so now what we've done is we've done 2 things. We've set the unhandled exception filter and we've patched system function 7. What does our exception filter do exactly? Well, the first thing I do is like, well, okay, if I get an exception, because there are times where other things in LSAS might throw an exception, like things like credential providers and stuff are like notorious for this. If the exception that's being thrown here is not illegal instruction, then I'm just going to say, continue the search, do something else. Just throw this up to the next exception handler in the stack of exception handlers. Okay, so then we've caught an illegal instruction. Now we're going to create, a string buffer, and we're going to copy some data into this string buffer. And that data we're going to copy, and you can already see what this says. User's password was changed to, and then I take and I find there's a string that's contained in RCX at this moment. Now, how did I know that? Like, how did I figure that out? How did I deduce that? And the answer is that, well, it's the ABI. That's how x64 works, is that when you call this function, at the moment that you enter this function, you would have your arguments, your parameters to this function already packed into specific registers, and that is RCX, RDX, R8, and R9, right? So in x64 or 64-bit Windows, your first, pointer sized arguments are always going to go into CD 8 and 9. And so I know that this is going to be in I take that back. I did it wrong. It goes backwards, right? So this, I believe, is RD X, and then hash is RCX. But you'll see that in my code, and I just now I'm realizing this right now live on screen. You'll see that I have compensated for my own miscalculation by doing a +8. And at first I was like not immediately sure like why I needed to do a +8, but I was inspecting the memory in the memory dump and I was like, I could see the password. It just happens to be 8 bytes past where I think it should start. Right. And the answer is, why is that? And I think it's because it's not actually in RCX. I think it's actually in R D. Oops, sorry. I think it's actually in RDX. Right. Because it's not left to right, it's right to left. We can fix that later, or maybe I'll just leave it there as a learning exercise, right? All right, but there's my password, right? It's in that register, and then I output it with output debug string, and then as we've already covered, I advance instruction pointer by 2, and then I tell us to continue. So what does all this mean? Now I'm going to show you the actual proof of concept here. Let's switch over to this different machine. This is a different machine. This is a Windows 11 desktop workstation. It's a standalone workstation. It's not a domain member. Yeah, Windows 11, 23H2. Um, First thing I'm going to do is I'm going to fire up. I'm going to fire up debug view, DBG view. Make sure you run this as administrator. And if you're a real hardcore sysinternals aficionado, you might be familiar. This is a very old sysinternals tool that basically allows you to easily view the output of output debug string across the system without needing to, have a debugger attached. So this is running and capturing. And so DBGView will catch all of my output. When I do output using output debug string, all that stuff should show up in DBGView. So I'll keep that in the background while I spawn a command prompt, CMD, have to run it as administrator. And then I stored the stuff in C :/x, right? Yes. So the first thing I have to do is I have to run the installer. I have to run the installer, and then I have to specify the path to my DLL, right? And so remember from the code that we just looked at, what this will do is it will inject hacks.dll into the LSAS process. Done. And now you'll see that the debug print statements, I'm inside your LSAS, hacking all your data, top level exception filter set, found crypt SP system function 7, and finally crypt system function 7 has been patched, just like we wanted. And I can use the same technique that I used earlier, task list -m hacks.dll, and I can see that, in fact, the LSAS process has now loaded my third-party DLL. This is looking very familiar to what that fancy, expensive enterprise-grade software does, right? But now, next, what I'm going to do is I'm going to take a look at net user, right? So net user lists all of the local user accounts on this workstation, and you'll see that I have a test user, right? Now, if I want to change test user's password, we'll do it like a net user test user, and then we'll change his password to something like um, dark mode 123 bang. Now, I don't think you need quotation marks either. So I'm going to do that. I'm going to hit, actually, let me make sure that my command prompt is out of the way first before I hit this. Sorry, I'm trying to get it positioned correctly so that you can see debug view at the same time. All right, when I hit enter, watch what happens. Okay, command completed successfully. And we'll see that sure enough, illegal instruction exception has been intercepted and user's password was changed to dark mode 123 bang. Now, this is just a proof of concept that just uses, output debug string, but in the real world, um, you could do anything that you could imagine. You could be writing this out to a text file. You could be uploading this to a database. You could be uploading this to a server on the internet. Literally anything that you could imagine you could do at this point. So this machine is now hacked. We're intercepting password changes, and if you want to see it done from another angle, you can do MMC, right? And we add snap in, we add local users and groups, local computer, finish, okay, okay. There is our test user right there. Let's change his password again. Set password, and then we'll change it to something else like, um, I don't know, I've been hacked, 123 bang. I'm not going to get the capitalization right on that. We'll just call it hacked, 123 bang, hacked, 123 bang. Okay. The password has been set, and you'll see, sure enough, user's password was changed to hacked 123 bang. Awesome. So we just hacked this machine. I hope you enjoyed, putting your red hat on and developing some malware. That basically brings me to the end of this. Let's make sure I showed you everything I wanted to show you. If I was internal, if like in my internal version of this that I presented at work, I have access to slightly, like I had access to the internal version of Mex and stuff that had a little bit more interesting things to show, but I don't have that here. Um, so I can't really show you that, but um, yeah, that's pretty much it. So I hope you enjoyed this. And I know it's been, 4 years since the last installment of dark mode. Hopefully it will not be another 4 years. Hopefully it will be much sooner than that. Um, as always, thank you very much for watching. If you have any comments, of course, I'm always open to any and all comments. Feel free to leave comments on the video. You can contact me. I don't use Twitter anymore like I used to. You can find me on Blue Sky. You can find me anywhere else. You can find me on GitHub, which is where I'll be posting the source code from this episode. Is on my GitHub, and that's all. So again, thank you very much for watching. Please subscribe, like the video, and I'll see you next time. Bye.